So in this problem, we're trying to solve the potential difference at point P here, which is this one. The question says, a thin circular ring of radius R, this is the radius, big R, capital R, carries a uniformly distributed charge Q. So the total Q is Q, which is distributed uniformly. Determine the electric potential at point P, which is this point, on the axis of the ring at distance x, this distance x, from its center, which is this one, this is the center, as shown in the figure. Okay, and now we're going to find the potential difference or electric potential at point P. And the total charge is Q, so we have total charge being Q, which is, in general, it is 2 pi r, which is the circumference of the circle of the ring, times lambda. Well, lambda is the linear charge density. Okay, lambda is linear charge density, which is Q divided by L. In general, it is Q divided by L, where L in this case is 2 pi big R. Okay? And now V is going to equal the integral of K, which is the constant, dq, the small slot on the ring, the small charge on this slot on the ring, divided by R. So what is R in this case? If we pick a point here or whatever on the ring, then we're going to connect this point to point P. This is going to be our R in this case. So this R is the hypotenuse of this triangle. If we call the angle to be theta, then this one is right angle triangle. Therefore, this one is hypotenuse. From the ring to the point P is hypotenuse. And we know that R squared equals X squared plus R squared. So X is constant, is not changing. From the center to the point is constant. And this R, the capital R, which is this one, is also the radius of the ring, which is constant. Therefore, R is going to be a combination of two constants, which is going to be a constant, a small r. Is going to be a square root of x squared plus r squared. And this one is constant. Because x is constant, r is constant. The radius is also constant. Therefore, here in this equation, k is constant, r is constant. We can take him out of the integral. And what is dq? dq is changing because q is very small here at this point, and then we're gonna take the integral of it, which means we're gonna sum it over all over this circumference of the ring. So we're gonna expand it. It's from 0 to total charge, which is big Q. And K divided by R, which is constant, goes outside. And this one is dq. Therefore, we're going to get K divided by R. And the integral of dq is just Q from 0 to Q. And this one is going to give us K over R times Q minus 0. Therefore, V is going to equal K big Q. Let me elongate this line. K big Q, which is the total charge, divided by R. And what is R in this case? This is K, Q, square root of x squared plus capital R squared. And this is our V. Let's box this one. Here. And then we can also solve it in another way. In this case, we're going to say that Q is lambda L, the total charge, of course. So what is L in this case? Is the circumference of the ring, which is lambda. Well, let me just write it on top here. Lambda times L, which is 2 pi big R. Therefore, Q is going to equal 2 pi R lambda. This is our Q, which is the total charge. And now let's write the equation for potential difference, which is the integral of K dq divided by R. So K is constant, R is constant, therefore we're going to have dq. But what is dq in general? If we break down Q, the charge, if we take a small point charge on this ring, then we're going to have dq is going to equal lambda dl, which is lambda ds, actually. But what is ds here? A small curvature on the ring, which is going to be, this small curvature is going to be r d theta, because r is constant, but theta keeps changing from 0 all the way to the same point, which is going to be 2 pi. This is r d theta. R is not changing because here is hollow. See, from the center right away to the ring. And in the middle, we don't have any charge. Therefore, the charges are accumulated here on this ring. And the distance here to the center is just R, which is the radius. And this is our dq. dq. And theta actually runs from 0 to 2 pi. So we're going to write dq in terms of lambda, r, and theta. This is k divided by r, lambda, r, d theta. And theta runs from 0 all the way to 2 pi. Therefore, we're going to get k lambda r divided by small r, and here the variable is going to be theta because theta keeps changing from 0 all the way to 2 pi. Therefore, we're going to have k lambda r, big R, divided by small r. And then here we have theta from 0 to 2 pi. In this case, we're going to get k lambda r divided by small r, 2 pi minus 0, which is going to be 2 pi. It's going to be 2 pi. Therefore, we're going to get k lambda times 2 pi r. Divided by small r. So 2 pi r lambda, which is this one, is nothing more than total charge, which is going to be k q, and this r is the hypotenuse, which is square root of x squared plus r squared. And this one is our v. So if we just take it a little bit down, and we can box this one as well. So it is here. If we compare these two, we're going to find them the same thing. So there are two ways of solving. And here we just said q is the variable, but here we said theta is the variable. And both cases, the answer boils down to the same thing.